Alright, is she working on Twitch? Hello. Here we go. Hey, there she goes. Oh, buddy. Looks like she's working there too. Good stuff. Let's pop this stuff out. Alright, alright. I'm gonna try and fill the dead air with random noises, and I do this every single time. I hate you too, but use something to redirect it. No way am I going back to that. Hey, Sorbet! How's it going? Glad to see you. Hello? I think my desktop audio might be coming through. No, 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 she ain't. She ain't. Good stuff. Good stuff. Right, where am I going? Uh, yeah, sure. Yeah. All right, I'm just gonna wait a few moments. Gonna get some tea going up. Just a moment. Gonna mute my video. I survived, by the way. I am still alive. I beat it. Honestly, I'm proud of myself. I'm so strong. Right, I believe here's where we were previously. I think maybe we got a... What happened? Ah, shoot. I think maybe we got to here. Maybe we got a bit further, honestly. I don't really know. I don't know. Ref cell of any type and the interior mutability pattern. I think I did get through this, but I may not have done the quiz. Shit. Just a minute while I figure this out. After we've created the list A, B, and C, we want to add 10 into the value. We can do this by mute. You know what? It'll be a refresher until I figure that out. I'm just going to start from the top. Going to start right out. It's been a bit, but you know. Let's start this up. Ref cell. This does look terrifying. We're more into memory management, which is scary no matter what. I've met 40-year-old people who are just 20, 25 years into this who still get scared every time they hit memory management. Alright, let's get into it though. Ref cell and the interior mutability pattern. I definitely have read this, but I'm going to do it again. Interior mutability is a design pattern in Rust that allows you to mutate data even when there are immutable references to that data. Normally, this action is disallowed by the boring rules. To mutate data, the pattern uses unsafe code inside a data structure to bend Rust's usual rules that govern mutation and borrow. Unsafe code indicates to the compiler that we're checking the rules manually instead of relying on the compiler to check them for us. We will discuss unsafe code more in Chapter 19. I really like that framing. That instead of the framing I normally see as, hey, you can just do whatever you want in unsafe code, they're stating, we are taking the burden of checking all of this information from the compiler onto ourselves. I like that. That is a good thing. I like that framing. It promotes a lot more caution. We can use types that, that's how it says. We can use types that use the interior mutability pattern only when we can ensure that the boring rules will be followed at runtime. Even though the compiler can't guarantee that. Oh, sorry. That is the end of the sentence. The unsafe code involved is then wrapped in a safe API, and the other type is still immutable. Let's explore this concept by looking at the ref cell type that follows the interior mutability pattern. Enforcing boring rules at runtime with ref cell of any type. Unlike RC, the ref cell type represents single ownership over the data it holds. So, what makes ref cell different from a type like box of any type? Recall the boring rules you learned in Chapter 4. At any given time, you can have either, but not both, one mutable reference or any number of immutable references. The references must always be valid. With references like box of any type, the boring rules invariants are enforced at compile time. With ref cell, these invariants are enforced at runtime. With references, if you break these rules, you get a compiler error. With ref cell, if you break these rules, your program will panic and exit. Use ref cell with heavy caution, because it will just crash your program. This is why it wasn't allowed into the Linux language for quite some time. They needed to have better ways of not just panicking. If that was placed into the compiler and there was some issue, we would have the issue we had with Cybershock recently, where a bunch of Windows computers just died. We really don't want that, so this is a very scary thing to be working with, I guess. Use this as little as possible is my takeaway. The advantages of checking the boring rules at compile time are that errors will be caught sooner in the development process, and there's no impact on runtime performance because all the analysis is completed beforehand. For those reasons, checking the boring rules at compile time is the... Sorry? Oh no. That doesn't matter right now. Right, sorry about that. For those reasons, checking the boring rules at compile time is the best choice for the majority of cases. This is why this is Rust default. This also makes compile times very, very lengthy, which is okay. The advantage of checking the boring rules at runtime instead is that certain memory safe scenarios are then allowed, where they would have been disallowed by the compiler time checks. Static analysis, like the Rust compiler, is inherently conservative. Some properties of code are impossible to detect by analyzing the code. The most famous example is the halting problem, which is beyond the scope of this book but is an interesting topic to research. I'm certain we can solve it, honestly. Because some analysis is impossible, if the Rust compiler can't be sure the code compiles with the ownership rules, it might reject a correct program, and this way, it's conservative. If Rust accepted an incorrect program, users wouldn't be able to trust in the guarantees Rust makes. However, if Rust rejects a correct program, the programmer will be inconvenienced, but nothing catastrophic can occur. The ref cell type is useful when you're sure your code follows the boring rules, but the compiler is unable to understand and guarantee that. Okay? I'm trying to think of an exact example where this might be the case. Perhaps where you have some input that's validated before it goes into your program, which if you get certain other input, like if you're adding stuff up but limited to 10, you can only add up to 10, it might do a buffer overflow or something similar to that. No, that could still work. I really don't understand exactly. I can't currently think of any case, but I can assume that there are quite a few cases. Similar to RC, RefCell is only for use in single-threaded scenarios, and will give you a compile time error if you try using it in a multi-threaded context. I wonder why. Low race conditions, but if we're giving the programmer this much access and ability, and we're allowing them to only utilize it when we know it would be safe, why separate the multi-threaded and single-threaded contexts? I mean, I don't understand that. We'll talk about how to get the functionality of RefCell in a multi-threaded program in Chapter 16. Here is a recap of the reasons to choose Box, RC, or RefCell. RC enables multiple owners of the same data. Box and RefCell have single owners. Box allows immutable or mutable borrowers checked at compile time. RC allows only immutable borrows checked at compile time. RefCell allows immutable or immutable borrows checked at runtime. Because RefCell allows multiple borrows checked at runtime, you can mutate the value inside the ref cell, even when the ref cell is immutable. Mutating the value inside an immutable value is the interior mutability pattern. Let's look at a situation in which interior mutability is useful and examine how it is possible. Interior mutability: a immutable borrow with an immutable value. A consequence of the borrowing rules is that when you have an immutable value, you can't borrow it mutably. For example, this code won't even compile. We have let x equal 5, this is immutable by default, and let y equal immutable reference to x. If you can try to compile it, it'll say, hey, you're an idiot. However, there are situations in which it would be useful for a value to mutate itself in its methods but appear immutable in other code. Code outside the value's methods would not be able to mutate the value. Using refcell is one way to get the ability to have interior mutability, but refcell doesn't get around the borrowing rules completely, which is good. The borrow checker in the compiler allows this interior mutability, and the borrowing rules are checked at runtime instead. If you violate the rules, you get a panic instead of a compiler error. Okay, I wish that it would outright state that this will have a massive amount of performance overhead. All those borrowing rules being checked with refcell in order to throw it a panic will, of course, be much less performant than just not using refcell or RC. Well, RC might be fine, actually. RC would be fine. Let's work through a practical example where we can use refcell to mutate an immutable value and see why it is useful. Why that is useful. A use case for interior immutability: mock objects. Sometimes during testing, a programmer will use a type in place of another type in order to observe particular behavior and assert it's implemented correctly. This placeholder type is called a test double. Think of it in the sense of a stunt double in filmmaking, where a person steps in and substitutes for an actor to do a particularly tricky scene. Test doubles stand in for other types when they're running tests. Mock objects are specific types of test doubles that record what happens during a test so that you can assert that the correct actions took place. That's really interesting. I like that. So instead of just having like 40 console logs, you can just have it auto-detail everything that happens. Rust doesn't have objects in the same sense as other languages have objects, and Rust doesn't have mock object functionality built into the standard library as some other languages do. However, you can definitely create a struct that will serve the same purposes as a mock object. Just like in C, how you don't have object orientation by default, but you can utilize the object-oriented paradigm quite simply once you understand how it really works. Which is one of my favorite things about learning C. I learned how object orientation actually works below the deck, without all these guardrails just allowing you to do it. Really understanding what you're doing helps me. Here's the scenario we'll test. We'll create a library that tracks a value against a maximum value and sends messages based on how close to the maximum value the current value is. This library could be used to keep track of a user's quota and the number of API calls they're allowed to make, for example. Our library will only provide the functionality of tracking how close to the maximum a value is, and what the messages should be at what times. Applications that use our library will be expected to provide the mechanism for sending the messages. The application could put a message in the application, send an email, send a text message, or something entirely else. The library doesn't need to know that detail. All it needs is something that implements a trait we'll provide, called messenger. Listing 1520 shows the library code. Alright, so we've got a public trait messenger with a send function. takes in self and a message, which is a reference string or a string slice. We have a limit tracker, a bunch of lifetime stuff, taking in a messenger of any type. All right, yep. No. Am I an idiot? That's not taking in. I can't remember what this is. This is oh, sorry, it must implement the trait messenger, I believe. Yeah, so the limit tracker struct must implement the trait messenger and holds the value messenger, value, and max, I believe. Implementing limit tracker with a lifetime of A and any type where T is where there's the trait messenger. Public function new messenger, taking in a messenger, which is a reference with an arbitrary lifetime and any type, as well as max, which is a usize. Outputting a limit tracker with the same lifetime and the same type. Okay? The new function will create a limit tracker with the messenger placed here, a value of 0, and the max given in. Okay? This still being implemented on limit tracker, you have another function called setValue, taking in a mutable reference to itself and the value, which is usize. Self.value will equal whatever value placed into it. It will create something called percentage of max, which equals just, well, the percentage, taking in the value and the maximum, dividing it. Percentage of max, if that is over 1, over or equal to 1, you're over your quota, is the error that will come up. If it is 90% or above, it'll give you an urgent warning. If it's 75% or above, it'll say, hey, here's a regular warning. Okay, so every single time a value is set, it will run this through, and within the messenger send this data, this information. And the messenger will be any trait, will be any code that can implement the .send. Where's the statement it must, yeah, okay. All right, pretty easy to understand, I guess. I'll admit I didn't understand each little part of that. I don't know why, honestly. One important part of this code is that the messenger trait has one method called send that takes an immutable reference to self and the text of the message. This trait is the interface that our mock object needs to implement so that the mock can be used in the same way as a real object. The other important part is that we want to test the behavior of the setValue method on the limit tracker. We can change what we pass in for the value parameter, but setValue doesn't return anything for us to make an assertion on. We want to be able to say that if we create a limit tracker with something that implements the messenger trait and a particular value for max, when we pass different numbers for value, the messenger is told to send the appropriate messages. We need a mock object for that. Instead of sending an email or text message when we call send, instead of sending, sorry, that will, okay, yeah. We'll only keep track of the messages it's told to send. We can create a new instance of the mock object, create a limit tracker that uses the mock object, call the setValue method on limit tracker, and then check that the mock object has the messages we expect. Listing 1521 shows an attempt to implement a mock object to do just that, but the borrow checker won't allow it. Alright, so we have a module test using super struct mock messenger as sent message, which is just a vector of strings. We implement mock messenger, which has a function new. we implement on mock messenger a function called new, which returns a mock messenger. Mock messenger is created with a set messages and an empty string. An empty vector. We implement messenger for mock messenger, a function called send, bringing in a reference to self and a message, which is a string slice. And the value here, what the function does is it simply pushes to send messages. All right. And then we have a test which creates the mock messenger, new mock messenger, let mutable limit tracker equal limit tracker new reference to mock messenger 100. Okay, the issue here, I'm guessing, is that we have an immutable reference here, and within itself, internally, it is attempting to mutate by adding to the string. We are not allowed to do this. Because, well, of course we're not allowed to do this. But we want to ensure that it is utilized in the same way, and thus can't change the code as much as we may want to. I believe that it will fail at this point. The test code defines a mock messenger struct that has a sent messages field with a vec of string values to keep track of the messages it's told to send. Also, why is that like that? We also define an associated type new to make it convenient to create new mock messenger values that start with an empty list of messages. We then implement the messenger trait for mock messenger so we can give a mock messenger to a trait limit tracker. In the definition of the send method, we take the message passed in as a parameter and store it in the mock messenger list of sent messages. In the test, we're testing what happens when the limit tracker is told to set value to something that is more than 75% of the max value. First, we create a new mock messenger, which will start with an empty list of messages. Then, we create a new limit tracker and give it a reference to the new mock messenger, a max value of 100. We call the setValue method on the limit tracker with a value of 80, which is more than 75% of 100. We then assert that the list of messages that the mock messenger is keeping track of should now have one message in it. However, there's one massive problem. Yeah. So cannot borrow self.sendMessages as mutable, as it is behind a reference. You are familiar with this? Help, consider changing that to a mutable reference, such as mutable reference to self. Self.sendMessages.push string from message. Self is a reference. So the data it refers to cannot be borrowed as mutable. We can't modify the mock messenger to keep track of the messages because the send method takes an immutable reference to self. We also can't take the suggestion from the error text to use a mutable reference to self instead, because then the signature send wouldn't match the signature in the messenger trait definition. Feel free to try and see what error message you'll get. This is a situation in which interior mutability can help us. We'll store the sent messages within a ref cell, and then the send method will be able to modify sent messages to store the messages we've seen. Listing 1522 shows us what that looks like. Alright, so we have use standard ref cell, we have struct mock messenger, sent messages is a ref cell holding a vector of strings. Implement mock messenger. We simply are creating a mock messenger with sent messages, which is a ref cell, : new, holding a vector, which is empty. Implement messenger for mock messenger. Send. It looks to be the same. Oh, no, never mind. We have self.sendMessages.borrow mutable. .push string from, and then whatever the message originally contained. Now this will work. It will assert equals, because we are utilizing ref cell, which utilizes unsafe code in order to allow us to mutate a value within itself, within the struct, where we wouldn't be able to before, because it is an immutable reference. using refcell to mutate an inner value while the outer value is considered immutable. The sent messages field is now of type refcell holding a vector holding strings instead of a vec holding strings. In the new function, we create a new refcell vector string instance around the empty vector. For the implementation of the send method, the first parameter is still an immutable borrow self, which matches the trait definition. We call borrow mute on the refcell vector string in self.sendMessages to get a mutable reference to the value inside the refcell vector string. Wow. Which is the vector. We can then call push on the mutable reference to the vector to keep track of the messages sent during the test. The last changes we have to make is in the assertion. To see how many items are in the inner vector, we call borrow on the refcell vector string to get an immutable reference to the vector. Now that you've seen how to use refcell, let's dig into how it works. Keeping track of borrows at runtime using refcell. When creating immutable and mutable references, we use the ampersand and ampersand mute syntax respectively. With refcell, we use the borrow and borrow mute methods, which are part of the safe API that belongs to refcell. The borrow method returns a smart pointer type ref, and borrow mute returns a smart pointer type ref mute. Both types implement the ref, so we can treat them like regular references. Okay, the refcell keeps track of how many ref and ref mute smart pointers are currently active. Every time we call borrow, the refcell increases its count of how many immutable borrows are active. When ref goes out of scope, the account of immutable borrows goes down by 1. Just like the compile time borrow rules, refcell lets us have many immutable borrows or 1 mutable borrow at any time. If we try and violate these rules, rather than getting compile error, as we would with references, the implementation of refcell will panic at runtime. Listing 1523 shows a modification to the implementation of send in 1522. We're deliberately trying to create 2 mutable borrows active with the same scope to illustrate that refcell prevents us from doing this at runtime. Okay, here we have just creating it twice, and then 1 borrow.push, string from message, 2 borrow.push. So here we are creating a mutable reference to self.senseMessages.borrowMute, and here we are doing it again. Where does it fail, I wonder? Does it fail when you try and create another one, or when we try and utilize it? I can't remember. We create a variable, 1borrow, for the ref mute smart pointer returned from borrow mute. Then we create another mutable borrow in the same way in the variable 2borrow. This makes 2 borrowable references in the same scope, which is not allowed. When we run the test for the library, our code in listing 1523 will compile without errors. However, the test will fail. So I see. This is why they're harking so heavily on test-driven development. Oh, okay, so you can have an immutable reference and a mutable reference, as long as only one of them exists at compile time. You can have as many... Right, so this has nothing to do with compile time. You can have as many immutable references as compile time, but as you try and run it, it'll panic. So, no. You have to follow the rules yourself at compile time. Runtime. Yeah, that is the case. You can have as many immutable references. You can have 32 immutable references, but only 1 mutable reference, as you can normally, but it won't warn you until the code is run, at which point it'll panic, crash, and die. Pretty useful, honestly. Right, here is the exact error. Where is it? Running failed, failures, yep. Panicked. Oh yeah, we don't get the error here, I don't think. Yeah. Notice that the code panicked with the message already borrowed, borrow mute error. Oh, it did have the error. Panic at already borrowed, borrow mute error. Okay, there it is. Notice the code panic there. This is how RefCell handles violations of the boring rules at runtime. So they have two implementations of checking the boring rules, one within RefCell itself and one within the actual uh, code of the compiler. I wonder how they differentiate those two things. Is the code duplicated, or do they simply call in some form of library with some alterations? Alright, let's continue. Choosing to catch boring errors at runtime rather than compile time, as we've done here, means you'd potentially be finding mistakes in your code later in the development process, possibly not until your code was deployed to production. Also, your code would incur a small runtime performance penalty as a result of keeping track of the borrows at runtime rather than compile time. However, using RefCell makes it possible to write a mock object that can modify itself to keep track of the messages it would have seen when you're using it in a context where only immutable values are allowed. You can use RefCell, despite its trade-offs, to get more functionality than regular references provide. Alright, however, I'm still going to argue quite heavily that outside of testing, where I do agree it is really good to use RefCell, that is correct. However, you could probably simply capture logging output for that specific case. With the exception of testing, you should avoid utilizing RefCell as much as humanly possible. I don't think I really have to say that. That's fairly understandable. Having multiple owners of mutable data by combining RC and RefCell, this is the thing that kind of shocked me that you were able to do. That breaks a lot of the ideas of Rust, I would think, but is something that I can see being needed. A common way to use RefCell is in combination with RC. Recall that RC allows you to have multiple owners of the same data, but it only gives immutable access to that data. However, with RefCell, you now have the ability to write with immutable access. If you have an RC that holds a RefCell, you can get a value that can have multiple owners and that you can mutate. For example, recall the cons list example in listing 1518, where we used RC to allow mutable lists to share ownership of another list. Because RC holds only immutable values, we can't change any of the values in the list once we've created them. Let's add in RefCell to gain the ability to change the values in the lists. Listing 1524 shows that by using a RefCell in the cons definition, we can modify the values stored in all the lists. Right, so you have an enumerable with a cons list, which is just cons, holding in RC, which holds a RefCell, which holds an I32 value. And of course, separately, the RC holding in list. A RC which holds in an enumerable list, or separately, the cons list, so the list can hold nil, nothing. Right, so we're utilizing the crate, list, cons, and nil, which was previously defined in the last chapter. Yeah, sure. As well as nil. Using the standard cell, RefCell. By defined, I meant it was utilized in the previous list. Sorry about that. We have used standard RC, RC. So currently we are utilizing cons and nil from the cons, from the list traits. From the lists trait. Sorry, from here. I'm an idiot. From here. I'm an idiot, yeah. So from the root of our project, we are utilizing, from the list definition, cons and nil. Okay, sorry about that. Utilizing standard cell RefCell, just bringing in RefCell and RC for our usage here. We have value, which equals an RC new, a new RC, holding a RefCell, a new RefCell, holding 5. So we have 5, which is being held within a RefCell, which is being held within an RC. Let A equal a new RC holding a new cons list, holding RC clone, a reference to our value. My god, that's a lengthy thing to say. as well as a new RC referencing nil. So this will be the end of the list, and this will be the value within the list. Cons holds an item stating that it is ending, as well as the value, or separately, a reference to the previous cons list item and value. As we see here, the item B holds a new RC holding a new ref cell holding the value 3, as well as a mutable reference, a reference to A. Okay, and then we have that again here. This is like a linked list, but less understandable somehow. No, actually, it's kind of more understandable, yeah. I kind of like it. I've never actually seen a cons list used. Right, so we dereference value dot bool mutable plus equals 10. So value, which is the first item, is now 15 because we are utilizing a ref cell. We are allowed to mutate the inner piece, and we are allowed to mutate it anywhere. Okay, yeah. So print A after A would be 15, 3, and 4. We create a value that is an instance of RC of type, holding a ref cell holding a value of I32, and store it in a variable named value so we can access it directly later. Then we create a list in A with a cons variant that holds value. You need to clone value so both A and value have ownership of the inner 5 value rather than transferring ownership from value to A or having A borrow from value. We wrap the list A in an RC, so when we create list B and C, they can both refer to A, which is what we did in listing 1518. After we've created the lists in A, B, and C, we want to add 10 to the value in value. We do this by calling borrow mute on value, which uses the automatic dereferencing feature we discussed in chapter 4 to dereference the RC to the inner ref cell value. The borrow mute method returns a ref mute smart pointer, and we use the dereference operator on it and change the inner value. Okay, that is a lot of complexity for what I believe to be a bit of a simple concept. I don't know how I could explain it too much better, honestly. But the RC holding a ref cell allows you to have multiple owners of something A. Let's say you had A, B, and C, all of which had a reference to this. You just had RC clone. Changing A, B, or C, using A, B, or C dot bool plus equals 10 would add 10 each time to the value original. That's a pretty simple concept, but I can understand why a person would be immensely confused because of just how much stuff is involved in this. Like, seriously, we have to say a new ref cell, which is being held by a new RC, which is being held in a cons list, which also separately holds the value, which is a clone reference to A utilizing RC. That's a massive sense. I can fully understand someone not understanding this. I think I do, though. When we print A, B, and C, we can see that they all have the modified value of 15 rather than 5. Oh yeah, sorry, I forgot. You're using pretty printing or whatever it's called to just print the entirety of A, B, and C. We're not going into the value section. I don't know why I thought that. But yeah. So we see here A after, it's just the value of 15. Here it's the value of 15, also holding the value of 3 and 4. It's just showing you that each shares the... Huh. Why is C like that? Where's 4? Where's 3? Oh, okay. Yeah, okay. Never mind. This cons list simply references A, not B. I see why. I'm curious, if you're still here, Sorbet, is this something that you're grasping? Is this something you're understanding? Again, I fully understand. If not, this is fairly strange of a way to. I don't see any better way to explain it, honestly. This technique is pretty neat. By using refcell, we have an outwardly immutable list value, but we can use the methods on refcell. Nope, fully understandable. I can't think of a better way to explain it, sadly. I think that the issue here that they're doing is they're using cons list. This could be much more understandable if they didn't just wrap all of this with cons list. That is the issue. I think this could be more understandable if we just had values A, B, and C. Let me see if I can just try and explain this in an easier way. What is it, .rs? I don't know. Sure. I'm just quickly going to try and explain this. Don't feel bad if you don't understand. I am going to see if I can experiment to see if I can explain this in a way just to cement the understanding in my mind. So let's just remove all values of cons. We don't need them. I'm an idiot. Right, and we definitely don't need this. Definitely don't need. Actually, yeah, we're just gonna have to go back to the start and delete it all. I don't know why I was trying to hold anything new. Right. Right, so, and let's have that be A. And this will also be value. Right? I'm surprised none of this is messing up. I'm guessing that there's something causing my LSP not to be running. Is my LSP running? I'm just gonna quickly check. Okay, it is, sure. Right, so what we are currently trying to do is have multiple references to the same thing, which can all be changed. In order to do so, we utilize refcell, which allows you to mutate something internally. It allows you to change the value within it, even if the reference is immutable. So an immutable reference states that you cannot change the thing within it. Refcell breaks that. So you cannot change what it's referring to. You cannot make value now equal a new object, like let value equal 5 equals 5. We can't do this. That will not work. RC will not allow this. Sorry, refcell will not allow this because this is an immutable for. However, we can in fact change the value within value, which is 5, to anything else that we want, utilizing the borrow mute method, allowing us to borrow it mutably. Now, we could not, in fact, borrow immutably two different objects. So right here, we have A and B. So if we tried to get B dot borrow mute, this would not work because we are trying to mutably change this listing here through both value, which is its own variable, and B, which is its own variable. However, and the reason for this is because of ownership. Right now, at this line, line 1, value is owned by value. But the second we clone it, the second Well, that's not usable. We don't actually need that. Sorry about that. Oh, well, that's quite useful. Wow, that was really helpful. Right, so a reference here would not work. If we did just this, A could not change. We can't use it here. We can't change it here because we can't change it here. A now owns value because we have a reference to value, a mutable reference, let's say, to value. We can't change it here because A now owns value. Value is no longer owned by value, but instead A. However, with RC clone, we can have multiple references which own the same thing. RC allows A to own value while still allowing value to own value. So, utilizing refcell, which allows us to change the internal piece, even if it's an immutable reference, along with RC, allows us to have multiple references. Each of them can change and own the same value. The same variable. Every single thing here has ownership. And using refcell allows us to change the interior value of every single one of them. I don't think that's a much better explanation, but I think that the confusion of cons makes it much more difficult. I hope that helps, but I can still understand if not. I guess the takeaway is if you want multiple things to be able to change the value inside, just wrap it in both an RC and a ref cell. Which can be quite useful, like, let's say you have a video game, and you have a team. There are 3 people on a team, and the team has 5 lives. If any member of that team dies, the value will be decremented. Now you want every single player to own this variable to allow you to take away from one of those lives. So, you give each ownership via a ref cell and an RC, so that when a player dies, the life is decremented. I'm glad that's better for you. Alright. Thank you for coming along with this, and allowing me to try and cement my understanding. Okay. Let's read forward. We create a value that is an instance of RC ref cell holding an I32. An RC holding a ref cell holding an I32, and store it in a variable named value, so we can access it directly later. Then, we create a list in A with a cons variant that holds value. We need to clone value, so both A and value have ownership of the inner 5 value rather than transferring out ownership from value to A, or having A borrow from value. We wrap the list A in an RC, so when we create lists B and C, they can both refer to A, which is what we did in listing 1518. After we've created the lists in A, B, and C, we want to add 10 to the value in value. We do this by calling borrow mute on value, which uses the automatic dereferencing feature we discussed in Chapter 4 to dereference the RC to the inner ref cell value. The borrow mute method returns a ref mute smart pointer, and we use the dereference operator on it and change the inner value. When we print A, B, and C, we can see that they all have the modified value of 15 rather. I read all of that. Again, my god. I read it all without even understanding I read it. I'm an idiot. What are you gonna do? Yeah, I've literally read all of this, actually. Alright, let's go on to quiz. Which of the following best describes the concept of interior mutability in Rust? Allowing the data on the inside of the data structure to be mutilated. Mutilated? I mean, sure, you can mutilate it if you want. Using the borrow checker to enforce memory safety at runtime. Nope. That's a ref cell? Interior mutability. That's part of it, but not the best description. Allowing data to be mutated to an immutable reference. I believe that's the correct one. Wrapping unsafe code in a safe API? No. I believe this is the correct one. Allowing data to be mutated through an immutable reference. I mean, allowing data on the inside of a data structure to be mutated it is true, but that could be done with immutable reference anyway. Here, I believe, is the correct answer. Consider an API that tracks the number of calls to a particular method. Struct API count with any number. API function of some method taking an immutable reference to self. Say the count is represented as a usize. Which of the following would be the most appropriate wrapper to use in this situation? I believe ref cell of a usize is fine. Currently, we have count, which needs to be incremented, and we have self, which is an immutable reference. If we wanted to increment this count, we couldn't, because it's immutable. We cannot, in fact, change self. Thus, in order to be able to change self while not making self mutable, we need a ref cell. Okay, consider the following incorrect implementation of a ref cell that does not check whether the interior value is borrowed. We have used standard cell, unsafe cell. Struct bad ref cell, taking an unsafe cell, implementing bad ref cell, function, public function borrow mutably, takes in a reference to self and outputs a mutable reference of any type. Unsafe, mutable reference, a dereference self dot zero, the first part of self dot get. I'll admit I don't actually know a lot about what this is doing. I'm guessing, well, the most of the reason is because of unsafe cell, so we can assume that dot get will simply get the value within 0. We're getting a mutable reference to whatever the dot get method provides us. Sure. Now say we have a bad ref cell like this. Let v equal bad ref cell, unsafe cell new, vector 1, 2, 3. So we pass into bad ref cell, which takes an unsafe cell, a vector of 1, 2, 3. Alright, so which of the following snippets would violate memory safety using this API? Okay. Alright, so let v1 equal v.borrow mutably. I don't even see where we're using ref cell. We're not using ref cell anyway. Unless ref cell is being used in get. I don't know. Anyway, v is the return of a bad ref cell. Okay, yeah, sure. Oh yeah, so this is running borrow mutably on v1. I see. So yeah, never mind. This isn't using ref cell at all. This is just asking about memory safety with this this new implementation of ref cell that doesn't check the safety rules. Right, so if we v1 dot borrow mutably, v1 equals v dot borrow mutably. So this is a new borrow. We have then n, which is a reference to the first value in v1. We then have v dot borrow mutably dot push 0. So we have two mutable borrows. But v1 is not used after this. Is it? Yes, it is, in n. I think this is the one that violates memory safety. Because we have, well, is it? Right, so no, v is utilized here, even though it is owned by v1. And then v1 is separately owned by n. So this is, I believe, the issue. This would violate memory safety, because you're mutating when you don't have the value to mutate. I believe. Yes. As well as N still being in life past the immutable borrow. Yeah, that is the operative. That's why it's broken. Right, second one, we have v dot borrow mute dot push 0, which is fine. We have n equals v dot borrow mutably, and then the 0th element. Then we have print line n. That's fine. V is destroyed. No, it's not. Yeah. The borrow mutable is destroyed here, but it still lives on because of ref cell. Same here. Yeah, that's fine. We have drop. That's not. Right, no, that's fine. We have drop v dot borrow mute. So what's happening here is we are borrowing a mutable reference to v, and then passing that into drop, which then destroys the thing that we just created. And then it does that twice. That's fine. That's meaningless code. Alright, so v1 dot borrow mutably, v2 dot borrow mutably, use v dot borrow mutably. I think that also does it. That also fucks it up. I mean, that's the one which makes the most sense to fuck it up. And then we utilize both to ensure that both are still in memory. Well, fuck. I'm unsure now. I believe both of these can cause the issue. Why is this not Because this is literally the original thing they showed us to show us that it would fuck up. I'm gonna have to say this, because this is literally what they showed us in the original piece. But I want to know why this isn't. Alright, let's see. Ah, I got one wrong. Maybe I was right originally, and the second one I still would be wrong, because I believe that is violating memory safety. Right? I want to just see the correct answers. Right, so question 1. Interior immutability is allowing the data to be mutated to an immutable reference. Context: the main idea of interior immutability is taking a value of type reference t and being able to safely mutate data within t. Reasonable. Question 2. We got this correct. We want a ref cell of resize. Here, a ref cell is useful to mutate an internal field, even though some method takes an immutable reference as input. If the internal field is just an integer, an even better choice would be the cell of usize, or atomic usize, which we have not gone over, but... Okay, yeah, so... Okay, yeah, fair. Atomic usize. I'm not going to go into that. Right, so... It is this one. It is this one. Apparently this is fun. Why is this fun? V2 has ownership, and then we're utilizing V1 to mutate with ref cell. The bad ref cell allows us to have 2 mutable references. Oh, because it's not violating memory safety. Not really. I mean, that is fine to do. Like, that isn't actually breaking anything. That's not going to cause any weird behavior. It's just, I was thinking of the boring rules and what ref cell would not allow. That is why that's in there. That's a gotcha. That's to fuck with you. I'm glad they put it in there. So this new implementation of ref cell does not actually check the boring rules, and thus, this is fine because there's no actual memory violation. Here, though, does directly violate memory. The bad ref cell allows us to have 2 mutable references on the underlying data at the same time, which permits a memory safety violation, like reallocating a vector while holding a reference to its contexts. Where is that done? Ah, here. How do I ban you? Delete, report, warn, timeout, ban, delete, ban. I think that worked. It's also delete. I don't think that's done anything. Ah, fine, who cares? The bad ref cell allows us. Yep. So I was correct at first. Good shit. Alright, that was quite interesting to learn. We still got an hour left before we head out. I think this is a reasonable amount of time to get through this. Ooh, that's nice. We got a picture here. That's exciting. I'm quite happy to see. How can I delete this message? Can I not? I'm gonna quickly check this out because I want to see. Oh, it's gone now. Well, thank you, Twitch chat. That's really kind of you. Okay. Thank you. I'm gonna try refreshing. I don't know what's going on. It's not refreshing. Sorry for this delay. I don't know if the stream is still working even. Okay. How about now? Are you going to work? Okay. I think it's working now. Let's try banning this guy. Hey, I think it worked now. Strange. Alright, I figured out why that was the case. I am utilizing some protective DNS stuff to ensure that trackers can't track me. I'm guessing that Twitch really wants to track me, so I had to stop doing that in order to ban a person. I guess tracking me is more important than spam. Either way, we're going to continue on like nothing happened. Good stuff. Reference cycles can leak memory. Rust memory safety guarantees make it difficult, but not impossible, to accidentally create memory that is never cleaned up. Really? Known as memory leak. Preventing memory leaks entirely is not one of Rust's guarantees. Really? I am shocked at that. Really? Meaning memory leaks are memory safe in Rust. Okay, well, yeah, they are, but like, I'm shocked to hear that memory leaks are just okay. We can see that Rust allows memory leaks by using RC and refcell. It's possible to create references where items refer to each other in a cycle. This creates memory leaks because the reference count of each item in the cycle will never reach 0. The value will never be dropped. Well, yeah. Yeah, okay, that is reasonable. I mean, that's on the guy making it. That's on the person who made it to make sure that you clean. Well, if there's still a reference, it's likely still being used. Don't have dead code. Let's look at how a reference cycle might happen and how to prevent it, starting with the definition of the list enum and a tail methods in listing 1525. Right, so we're utilizing from our crate list cons and nil. Back to the cons list, thank you. We have a standard cell of ref cell, we have a standard RC. We have an enum called list with, well, we just have a cons list being created here. We implement list with the function tail. We implement onList the function tail taking a reference to self, which returns an option holding a reference to a ref cell, holding an RC, holding a list object. We match self when it is a cons list with anything in it, and secondarily an item. We return a sum option of item. When it is nil, we return nothing. We return the none option. So this is checking whether or not we are at tail, the end of a cons list. A cons list definition that holds a ref cell, so we can modify what a cons variant is referring to. Sorry, just a moment, I'm going to check something. I need to check to see if that is something that happened. Where would that be? Just a moment, really sorry for this. Well, this is quite an engaging time, aren't we? How do we check that? Yeah. Whoops. Is there a search feature on here? I really just want to make sure that I didn't accidentally do something. Not very helpful, is it? You know what? Fuck it. Ah! We're using another variant of the list definition for listing 15.5. The second element in the cons variant is now refcell RC list, meaning that instead of having the ability to modify the I32 value as we did in listing 15.24, we want to modify the list value a cons variant is pointing to. We're also adding a tail method to make it convenient for us to access the second item if we have a cons variant. Oh, okay, that's what the tails method is doing. I'm an idiot. Takes in self. Who cares? No, I care. Yeah, it takes in self, and then self. If self is a cons item. Oh, I understand now. I'm a bit of a fool. Right, so what this is doing is matching on self, which is this cons list. If it has a secondary item inside of it, and that secondary item is not nil, then we return the secondary item, the next item in the list. Alright, in listing 1529, we're adding a main function that uses the definition in listing 1525. This code creates a list in A and a list in B that points to the list in A, and then modifies the list in A to point to B, creating a reference cycle. There are printline statements along the way to show what the reference counts are at various points in the process. Okay, so we have let A equal no RC, holding a cons list. We then print RC strong count, passing in a reference to A. That'll be 1. Print line, any next item, we then run tail. That'll be nil. It'll run out the none option. You get nothing. Let B equal, same deal. We have a RC new cons ref cell new RC cloned add A. Print line, a RC count after B creation. B strong count reference A. Right, so we are checking the count of A and the count of B and tail. I believe B will be 2. Sorry, A will be 2. B will be 1. And the tail will be, of course, A. We then have if let sum link equals A.tail, dereference link.borrowMutable equals RC clone reference B. Right, so sum link will equal. God, if let sum, I've kind of forgotten. I believe that link is being created if the value is sum from option. E will equal a.tail. I don't understand what's going on. I'll admit. I've once more forgotten what the if let does. Uncomment the next line to see that we have a cycle. It will overflow the stack. Print line. A next item equals a.tail. Right, so the count is, I'm guessing 2, and that's 3. All right, so what's going on here is that we have an item, and then we have an item which refers to the original item. Then we have an item which refers to, I don't know. Okay, yeah, as long as there's something within. Okay. Oh yeah, if it's not this, it does this. I remember, yes. So if tail returns a non-variant, then this is what it'll have. Thank you for that. Right, so we just have an item that refers to an item which refers to itself. So it creates a variable from what inside sum. Yep. So link is being created. If a.tail returns a sum variant, link will equal a.tail. If it doesn't return a sum variant, it'll equal whatever is here. Okay. Thank you for that. Sorry about that. Right. So that'll equal B, a clone of B. So now A is equal to B and B is equal to A. That is the current case, which is a reference cycle. All right. We'll create an RC list instance. Thank you, by the way, Sorbet. I can't imagine why I can't get that in my head. We create an RC list instance holding a list value in the variable A with an initial list of 5 and nil. We create an instance of RC list. We create an RC list instance holding another list value in the variable B that contains the value 10 and points to the list A. We modify A so it points to B instead of nil, creating a cycle. We do that by using the tail method to get a reference to the ref cell RC list in A, which we put in the variable link. Then we use the bool mute method on the ref cell RC list to change the value inside from an RC list that holds a nil value to the RC list in B. When we run this code, keeping last println commented out for the moment, we'll get this output. We'll get A, initial ref count equals 1. A next item is a ref cell and the value nil. A RC count after B creation is 2. B initial RC count is 1. I was correct on that. B next item is the sum ref cell holding the value 5. That is A. The previous value is not A. I don't know what that is actually. B RC count after changing A is 2. A RC count after changing A is 2. Okay. The reference count of the RC list instance, both A and B, are 2 after we change the listing in A point to B. At the end of main, Rust drops the variable B, which decreases the reference count of the B RC list instance from 2 to 1. The memory that RC list has on the heap won't be dropped at this point, because its reference count is 1, not 0. Then Rust drops A, which decreases the reference count of the A RC list instance from 2 to 1 as well. This instance's memory can't be dropped either, because the other RC list instance still refers to it. The memory allocated to the list will remain uncollected forever. To visualize this reference cycle, we've created a diagram in figure 1514. B refers to 10, which also holds a reference to 5, which also holds a reference to 10, which also holds a reference to 5. A holds a reference to this entire object, which again has this cycle. Okay. If you uncommented the last print line and run the program, Rust will try to print this cycle with A pointing to B pointing to A and so forth, until it overflows the stack. Compared to a real-world program, the consequences of creating a reference cycle in this example aren't very dire. Right after we create the reference cycle, the program ends. However, if a more complex program allocated lots of memory in a cycle and held onto it for a long time, the program would use more memory than it needed and might overwhelm the system, causing it to run out of available memory. That's a memory leak. Creating reference cycles is not easily done. You have to go. Thank you for your time. Talk to you later. Creating a reference cycle is not easily done, but it's not impossible either. If you have a rough cell value that contains RC values or similar nested combinations of types with interior immutability and reference count, you must ensure that you couldn't create cycles. You can't rely on Rust to catch them. Creating a reference cycle would be a logic bug in your program that you should use automated tests, code reviews, and other software development practices to minimize. Another solution for avoiding reference cycles is reorganizing your data structures so that some references express ownership and some references don't. As a result, you can have cycles made up of some ownership relations and some non-ownership relations. And only the ownership relations affect whether or not a value can be dropped. In listing 1525, we always want cons variants to own the list. Fuck. Shit. Sorry about that. I'm just going to continue on. I'm going to go to the next one anyway. I think I understand what's going on. No, let's reread this entire paragraph. Another solution to avoiding reference cycles is reorganizing your data structures so that some references express ownership and some references don't. As a result, you have cycles made up of some ownership relations and some non-ownership relations, and only the ownership relations which affect some whether or not a value can be dropped. Listing 1525, we always want cons variants to own their lists. So reorganizing the data structure is not possible. Let's look at an example using graphs made up of parent nodes and child nodes to see when non-ownership relationships are appropriate ways of preventing reference cycles. All right. Yeah, down we go. Down we go. Down we go. Right. Where were we? So far, we demonstrated that calling RC clone increases the strong count of an RC instance, and an RC instance is only cleaned up once its strong count is 0. You can also create a weak reference to the value within an RC instance by calling RC downgrade and passing a reference to the RC. Strong references are how you can share ownership of an RC instance. Weak references don't express an ownership relationship, and the count doesn't affect when an RC instance is cleaned up. They won't cause a reference cycle because any cycle involving some weak references will be broken once the strong reference count of values involved is 0. When you call RC downgrade, you get a smart pointer of type weak. Instead of creating the strong count in RC instance, instead of increasing the strong count in RC by 1, calling RC downgrade increases the weak count by 1. The RC type uses weak count to keep track of how many weak references exist, similar to strong count. The difference is the weak count doesn't need to be 0 for the RC instance to be cleaned up. Because the value that weak references might have been dropped to do any because the value that weak references might have been dropped. What? Because the value that weak references might have been dropped to do anything with the value that a weak is pointing to, you must make sure that value still exists. Yes. Do this by calling the upgrade method on a weak instance, which will return an option RC type D. You'll get a result of sum if the RC value has not been dropped yet, and a result of none if the RC value has been dropped. Whereas upgrade returns an option, Rust will ensure that the some case and the none case are handled, and there won't be an invalid pointer. As an example, rather than using a list whose items know only about the next item, we'll create a tree whose items know what their children annihilate. Creating a tree data structure, a node with child nodes. To start, we'll build a tree with nodes that know about the child nodes. We'll create a struct named node that holds its own i32 value, as well as a reference to its children node values. Use standard cell ref cell as an RC. We get a derived debug node with the value, which is 932, and the children, which is a ref cell holding a vector, which holds RCs holding a node struct. Right. We want a node to own its children, and we want to share that ownership with variables so we can access each node in the tree directly. To do this, we define the vec item to be values of type RC. We also want to modify which nodes are children of another node. So we have a ref cell in children around the vec RC node. Next, we'll use our struct definition to create one node instance named leaf, with the value 3 and no children, and another instance named branch, with the value 5 and leaf as one of its children, shown in listing 1527. Function main, let leaf equal an RC new, holding a node, holding value 3, children, ref cell, back new. Yep, branch. It's another branch. Holding an RC new, holding a node, value 5, children, ref cell, back new, RC clone of leaf. Goddamn. We clone the RC node in leaf and store that in branch, meaning the node in leaf now has two owners, leaf and branch. We can get from branch to leaf through branch.children, but there's no way to get from leaf to branch. The reason is that leaf has no reference to branch and doesn't know they're related. We want leaf to know that branch is its parent. We'll do that next. Adding a reference from a child to its parent. To make the child node aware of its parent, we need to add a parent field to our node struct definition. The trouble is in deciding what the type of parent should be. We know it can't contain an RC, because that would create a reference cycle with leaf parent pointing to branch, and branch.children pointing to leaf, which would cause their strong count values to never be 0. Thinking about the relationship in another way, a parent node should own its children. If a parent node is dropped, its child node should be dropped as well. However, a child should not own its parents. If we drop a child node, the parent should still exist. This is a case for weak references. So instead of RC, we make the type of parent weak, specifically a ref cell weak node. Now our node struct definition looks like this. Simply have a node that is a parent, God, what is that? Parent property, whatever, of type ref cell holding a weak, holding a node. Weak is brought in from standard RC. A node will be able to refer to its parent node, but doesn't own its parent. In listing 1528, we update main to use this new definition so the leaf node will have a way to refer to its parent branch. Let leaf RC new node, yep, leaf.parent.borrow.upgrade. Okay, yeah, this is gonna have some massive chaining, ain't it? That's how you print out the parent. You have to borrow it and then .upgrade it. Fantastic. I'm glad for that. That's great. Standard out.print line, my friend. I'm glad that they took some references from Java, taking their homework a little bit. Alright, right. Branch equals RC new node, value 5. Parent is ref cell, new, weak, new. With nothing inside of it, it's a ref cell so that we can change the weak value here. Leaf.parent.borrowMute equals RC.downgrade branch. I'm going to say dot for this from this point forward. I don't think I'm ever not going to. Double colon, I don't know what to say. A leaf node with a weak reference to its parent node branch. Creating the leaf node looks similar to the listing 1527, with the exception of the parent field. Leaf starts out without a parent, so we create a new empty weak node reference instance. At this point, when we try to get a reference of the parent of leaf by using the upgrade method, we get a none value. We see this from the output of the println statement. Leaf parent equals none. When we create the branch node, it will also have a new weak node reference in the parent field because branch doesn't have a parent node. We still have leaf as one of the children of branch. Once we have the node instance in branch, we can modify leaf to give a weak node reference to its parent. We use the borrow mute method on the ref cell weak node in the parent field of the leaf. Then we use the RC downgrade function to create a weak node, referring to the branch from the RC node in branch. Here's where we do this. Leaf.parents.borrow mutably, because of the ref cell, now equals RC downgrade a reference to branch. Alright. When we print the parent of leaf again, this time we'll get a sum variant holding branch. Now leaf can access its parent. When we print leaf, we can also avoid the cycle that eventually ended in a stack overflow like we had in listing 15 step 26. The weak references are printed as weak. Leaf parent node value 5 ref cell value weak. Yep. Okay. The lack of infinite output indicates that this code didn't create a reference cycle. We can also tell this by looking at the values we get from calling RC strong count and weak count. Visualizing changes to strong count and weak count. How much further are we going? Okay. Let's look at how the strong count and weak count values of the RC node instance change by creating a new inner scope and moving the creation of branch into that scope. By doing so, we can see what happens when branch is created and then dropped when it goes out of the scope. The modifications are shown in listing 1529. You simply have this, which creates all of that information and then prints out a bunch of information about it. After leaf is created, its RC node has a strong count of 1 and a weak count of 0. In the inner scope, we create branch and associate it with leaf. At which point, when we print the counts, the RC node in branch will have a strong count of 1 and a weak count of 1 for leaf.parent pointing to branch with a weak node. When we print its counts, when we print the counts in leaf, we'll see it will have a strong count of 2 because branch now has a clone in the RC node of leaf stored in branch.children, but will still have a weak count of 0. When the inner scope ends, branch goes out of scope and the strong count of the RC node decreases by 0 to 0. Decreases by 1 to 0. So its node is dropped. The weak count of 1 from the leaf.parent has no bearing on whether or not node is dropped, so we don't get any memory leaks. If we try to access the parent of leaf after the end of the scope, we'll get none again. And at the end of the program, the RC node in leaf has a strong count of 1 and a weak count of 0, because the variable leaf is now the only reference to the RC node again. All of the logic that manages the counts and values dropped is built into RCT and weak T, and their implementations of the drop trait. By specifying that the relationship from a child to its parent should be a weak reference in the definition of node, you're able to have parent nodes point to children nodes and vice versa without creating a reference cycle and memory leaks. Summary. This chapter covered how to use smart pointers to make different guarantees and trade-offs from those Rust makes by default with regular references. The box type has a known size and points to data allocated on the heap. The RC type keeps track of the number of references to data on the heap, so that data can have multiple owners. The ref cell type, with its interior mutability, gives us a type that we can use when we need an immutable type, but needs to change an integer value of that type. It also enforces the boring rules at runtime instead of at compiling time. We also discussed were the deref and drop traits, which enable a lot of the functionality of smart pointers. We explored reference cycles that can cause memory leaks and how to prevent them using weak. If this chapter has piqued your interest and you want to implement your own smart pointers, check out the Rustonomicon for more useful information. Next, we'll talk about concurrency in Rust. You'll even learn a few new smart pointers. Right, so we simply have a question, will this compile, and if so, what does it do? We use a standard RC, let R1 equal an RC into 0. RC, right, okay. Let R4 equal a new context, a new, what is it called? Yeah, new thing. We are letting R2 equal RC clone R1, a reference to R1. So R2 does not, sorry, R2 owns R1, along with R1 also holding and owning R1. We then downgrade RC downgrade R2. R2 is now a weak reference. And then we pass it back to R4. Okay. Does R2 get deleted? I'm unsure. Let R5 equal RC clone R1. I guess we'll learn soon. This wouldn't be useful syntax if it did. No, it would. It definitely would. You could pass back values. Let R5 equal RC clone, a reference to R1. So R5 also owns it. So strong count is now 2. Strong count is now 1. R5 equals RC clone R1. Strong count is 2. R5, saying owned reference to R1. And then R6 equals R4 dot upgrade. R6 is now a strong reference to R1. Print line. RC, strong counter of R1, and a weak counter of R1. I think this does compile. And we're simply looking for the strong and weak counters. Reasonable, right? So we have one strong counter here. Here, we have 2 strong counters, but downgrade decreases it back to 1. Right. R4 is now weak count. So that's 1 weak, 1 strong. R5 is RC clone R1. That's 2 strong counts. And R6 is a strong count with R4 dot upgrade. I do believe that upgrade, because it's a dot, I can't remember what that is. It's not a method, it's a whatever. It can't actually change R4. R4 cannot be mutated. No, it's an immutable reference. R4 cannot be mutated, and thus R6 is simply a reference in and of itself. So R6 is a strong counter. So that's 1, 2, 3 strongs. And that's 1 weak. We have 3 space 1, I believe. Yep. Submit. Hey, you got that correct. The 3 strong refs are R1, R5, and R6. The 1 weak ref is R4, which is dropped at the end of main. R2 is dropped at the end of its scope. Yep, R2 no longer exists. Alright, this is fearless concurrency. We're going to read that next time because we're not going to get into concurrency today. Okay, getting closer and closer to the end. Exciting times, exciting times. So what are we going to do next? But that's it for today. Goodbye. Love you.